Okay, so we're in Chapter 8 now, and the focus of Chapter 8 is on systems of linear differential equations. We've already done a little bit of work with this, both in Chapter 4, where we talk about solving systems of linear DEs using elimination, and in the previous section, section 7.6, where we used Laplace transforms to solve some linear systems. This section is going to treat the topic a little bit more generally and take kind of a linear algebra sort of approach to solving these systems. And once again, as we've said in this class, linear algebra is not a prerequisite for this course. However, you will absolutely benefit if you've had it before. So these concepts will probably come a little bit more naturally if you've been through a linear algebra course. Now, I will preface this entire chapter by saying, even though you don't need to have had linear algebra for this course, I am going to be assuming that you have some familiarity with working with matrices, because we are heavily concerned with matrices in this section. That's kind of one of the primary tools that we're using when we're looking at these systems. In particular, things that you need to know how to do with matrices. You need to know how to add and subtract matrices. You need to know how multiplication by a scalar works with matrices. We just call that scalar multiplication. And you also need to know how two matrices, what it looks like to multiply two matrices. In particular, multiplying a matrix by a column matrix or a column vector. So if those are things that you're not very familiar with, as we go through this section, if you're kind of unclear on, why are we representing a system of linear DEs using this matrix multiplication thing that we're doing here, if that's not making sense to you, you may want to do a little bit of study on your own of matrices. If you want, you can go look at my linear algebra videos. Section 1.3 in those videos, I believe, talks about operations with matrices. That can help you kind of, just familiarize yourself with some of the stuff that we're using here. But because there's a lot to talk about, we're not going to review, basics with matrices. I'm going to just assume that you have some familiarity there. So that's my first disclaimer. The other one, which I'm not really, I don't think calling it a disclaimer is going to make much sense, but this section is very similar to 4.1. In fact, I think the title of this section is almost the same as 4.1. In 4.1, we dealt with the kind of theory behind linear differential equations. And we derived a lot of results. We talked about linear independence and linear dependence. We talked about the Wronski in there. We talked about fundamental sets of solutions for homogeneous equations and complementary and particular solutions for non-homogeneous equations. And in this section, we're kind of dealing with a lot of the same stuff, but it's those same concepts applied to systems of equations now as opposed to just a single equation. So for that reason, because we're kind of going over a lot of concepts that we've sort of already addressed in 4.1, we're probably going to move through those a little bit quicker. We need to make sure that we understand how they work in the context of systems of equations, but you're going to see a lot of terms that you should be familiar with already that came straight out of 4.1. So you'll notice this section feels very similar. Let's go ahead and get into it. So, like I said, we're dealing with systems of linear differential equations in this section, in this chapter. We're going to define a first-order system as a system of differential equations like what we have here, wherein each of those equations is a first-order equation. And in particular, we're going to be seeing them take this form. So the derivative of each of your variables will appear on the left. On the right, you'll get some function of each of the unknown functions of t and possibly a function of t itself. But notice this representation of a system doesn't actually imply that we're dealing with linear DEs. Depending on what this function looks like on the right-hand side, this may be nonlinear. So this is just to say what a first-order system of DEs looks like. Then, to be more specific, the kinds of functions we're looking at in this section are going to be linear. So the systems that we're going to be tackling will have a form something like this. dx1 dt equals, now notice on this right-hand side, we have a linear expression in the unknowns x1 through xn, and then plus some other function of t, which may or may not appear there. This function may be 0, it might be something else. But that's what each of the equations looks like. Okay, pay close attention to the notation that we're using for the subscripts on these a's here. So it's two values indicating which equation the coefficient is appearing in, and then which unknown it's being multiplied to. So for example, a11, this one implies that this coefficient belongs to the first equation. This one implies that it's being multiplied to x1. For example, if I come down here, this an2, the n implies that this is the coefficient, this is one of the coefficients appearing in the nth equation, and the 2 implies that it's the coefficient being multiplied to the unknown x2. Okay, so this lends itself naturally to entries in a matrix, if you're familiar with that notation. Now, this, like it says here, we're going to be calling this a system of equations that's been put into this form, normal form. What we want to do is take a system of equations that's been put in normal form and convert it into what we call matrix form, and that's what we're going to develop down here. So, now, in the event that these f1 of t, f2 of t, all of these f of t functions that are appearing here, if all of those are equal to 0, then we will say that the system is homogeneous. Notice the connection to homogeneous equations that we talked about in chapter 4. If that's not the case, then the system is going to be non-homogeneous. Now, notice in order for the system to be non-homogeneous, all it takes is one of these functions to be non-zero. It's possible that all the others are 0, but as long as at least one of these f's is non-zero, then we have a non-homogeneous system. Okay? And what we're going to do is define some matrices now that are going to help us relate back to this system of equations. So one thing to notice here is that when we're dealing with matrices in this section, the notation that we're going to be using is capital bold letters. So capital bold X, capital bold A, capital bold F. We're going to be seeing those a lot here. This X will denote this matrix here. Now notice this is a column matrix, meaning it consists of only one column, but n entries. And the entries in this column are exactly the functions of t that we're trying to solve for in our system. So in this system of equations, you would be trying to solve for x1, x2, all the way through xn. All of those are loaded into this column matrix, which we're going to be calling x. So this x is, think of this as the thing that we want to be solving for in a system of equations. Now this guy, this A of t, is a bigger matrix. This is an n by n matrix, meaning it has n rows and n columns. The n rows correspond to the n equations in this system. The n columns correspond to the n unknowns in the system. And in case you didn't notice, I didn't mention this, but there are the same number of equations here as there are unknowns. And that's important because it's in those specific cases that we can apply the techniques that we're going to talk about in this section. Okay? So n by n matrix, and the entries in this matrix are exactly those coefficient functions. a11 of t is appearing here. a12 of t is appearing here. Okay, so because of that, A is commonly referred to as a coefficient matrix. And that's the terminology I'm going to use here. Finally, all of these f functions here, these functions of t that are appearing at the end of these equations, also end up in their own column matrix, and we're going to call that capital F of t, or just capital F. Sometimes we leave the of t off. Okay. Notice also that if this is a homogeneous equation system, then this will be a column matrix consisting only of zeros. Okay. So we can take these matrices and operate on them in such a way that the resulting equation is a representation of this system of equations. And what we're looking at specifically is this. So notice, let me come back up here to the system of equations. If I look at what's showing up on the left-hand side of each one of these equations, it's the derivative of x1, the derivative of x2, and so on and so forth, all the way down to the derivative of xn, all with respect to their variable t. Notice that if I were to take this column vector right here, column matrix, column vector is another term for a column matrix, and if I were to just differentiate each entry with respect to t, then what I would get is a column matrix with these entries in it. So one way of denoting that in a matrix is to simply write d dt of the entire matrix. And what this is notation for is, because you may think, what does it mean to take the derivative of a matrix? Well, literally what we're talking about is taking the derivative of each of its entries, respectively, with respect to t. So this left-hand side gives us a column matrix representing the left-hand side of each of these equations. We set that equal to this, our coefficient matrix times the column vector, or the column matrix, that we define to be x right here. Because if you know how multiplication with matrices works, remember this is something I said that I'm assuming you have some familiarity with. We take this column matrix, and I like to think of it as kind of lifting it up and turning it 90 degrees and then dropping it down on each row of this coefficient matrix, multiplying the things that land on each other and then summing the results. That's how multiplication with matrices works. Then what we would end up with is a matrix whose entries exactly match the right-hand side of these equations except for these f's. So it would give us everything in here by performing this multiplication down here. Finally, to get these plus f1 plus f2 and so on and so forth that's appearing on the right-hand side here, we need to add another column matrix that gives us exactly those functions, f1 of t, f2 of t, and so on and so forth. Writing this in this way and then using the notation that we talked about previously, the right-hand side of this equation is just ax plus f, which I'm seeing right here, ax plus f. Okay, this guy right here, which I'm calling d dt of that matrix x, we're going to use the notation x prime to denote that, the column matrix consisting of all of those derivatives. And so what that does is it takes this fairly complicated and involved system, maybe complicated is not the right word, but it's a lot to write down if you're going to write all of this. And it gives us a much more compact notation for the same system of equations. We can simply write it this way, understanding x prime, a, x, and f to be what we defined up here. In the event that the system is homogeneous, then this f is a zero matrix, and this thing simplifies even further to x prime equals ax. So this will be what a homogeneous system of equations looks like in matrix form. Okay? So let's do a couple of examples where we're given systems of equations, and what we want to do is write them in matrix form. So looking at the systems that we have here, I have dx dt and dy dt. So my two unknowns are x and y. That means that the column matrix x here, instead of looking like x1, x2, x3, and so on, it's just going to be xy. That's what it's going to look like. My coefficient matrix is going to be exactly the coefficients on my x's and y's, those unknowns. So I know that this left-hand side, taking the left-hand side of each of those equations and putting them into a column matrix, is going to be what we're calling x prime. And then I set that equal to ax. A, in this case, is the coefficient matrix, so I just create a matrix out of the coefficients in the same order that I see them. So 6, negative 9, negative 1, positive 2, negative 1, 2. And then this guy right here is x, okay? And then finally, there's no additional functions of t that are being added to either of these equations. So that makes this a homogeneous system of equations, which means my system should take this form. X prime equals a coefficient matrix times x. This is the matrix form of that system. One thing to note here is that when we talk about the matrix A, I'm actually writing that matrix explicitly. I'm putting the coefficients in there so I can see them. But when we talk about the matrices X and X prime, I'm not writing that as the column matrix XY, and I'm not writing this as the column matrix dx dt and dy dt, even though that is what they represent. I just write this as X and X prime. That's typical of writing these systems. Okay, let's look at a 3x3 system, which is a system of 3 equations with 3 unknowns. Same idea. This time my column matrix is my column matrix X will consist of X, Y, and Z as its entries, but I'm still going to just refer to the left-hand side as X prime. Now this X prime and this X prime are different matrices because this one is a 2x1 matrix consisting of the entries X and Y. This is a 3x1 matrix consisting of the entries X, Y, Z. Even though they look the same, we understand from the context of where they came from that they represent different matrices. Okay, so that's important. When you see this X or X prime, exactly what that equals depends on where it came from in the first place. We just keep that in the back of our minds. Now, what is our coefficient matrix? This time it's going to be a 3x3 matrix instead of a 2x2 matrix. And remember, we're only looking at the coefficients on the unknowns, x, y, and z. So here I have 1, -1, +1. So 1, -1, 1. Looking at my second equation, x is not appearing in this equation. So I'm imagining there being a 0x here. The coefficient on x is 0, on y it's 1, and on z it's 4. Down here I have an x and I have a z, but I'm missing a y. So on my x I have a coefficient of 2, on my y I imagine a coefficient of 0, and on my z I have a coefficient of 2. Then the x appears here. In this system of equations we do have functions of t appearing on each of these equations. And so this is a non-homogeneous equation, and I need to do that plus f matrix. However, because f consists of different functions of t, I'm going to write that explicitly so I can see what those functions look like. E to the t here, -t squared here, t minus 5 here. Okay? So this would be the matrix form for this system of equations. All right. I think we'll go to the end of this page, and then we'll probably stop this video and do a part 2 after this. So here's that matrix again, that capital X that we defined on the previous page, which consists of, its entries consist of all the functions that we're trying to solve for in our system. Okay. Now, any column matrix that has this form, if it satisfies this system of equations, remember this is the matrix form for a system of equations, then we refer to this thing as a solution vector. In particular, if it satisfies this on a particular interval I, then we say that this is a solution vector to this system on that interval I. Okay? And we're going to single out the case of a 2x2 system just for a second. We're going to be primarily looking at 2x2 systems and some 3x3 systems in this chapter. But let's suppose that we have a solution vector for a 2x2 system of differential equations. Then the solution vector will be a 2x1 matrix because there's only 2 unknowns to solve for, x1 and x2. Now, if we think of these equations, this x1 of t and x2 of t, they're both functions of t, we can think of them as parametric equations for a curve in the plane. So if we set x equal to x1 of t and y equal to x2 of t, then these parametric equations correspond to a curve in the plane. And that curve is what we call a trajectory. Okay, we're not going to use this term much in this section, but it'll come up in the next section. So we're just introducing the term here. The plane in which that curve exists is called the phase plane. So just making note of that notation here, and we'll elaborate on that in the next section. Let me go ahead and stop this video here, and we'll continue on in the next.